Hi everybody, welcome to Guidancee Education channel. We are continuing class 11 chemistry, chapter 3 classification of elements and periodic properties. This is periodic properties part 3. We will be discussing atomic radius and variation of atomic radius along the period and down the group. And along with this, we will give more stress to the reason for decrease in atomic radius across the period, anomaly in atomic radius of nitrogen and oxygen, increase in atomic radius of zero group elements, and increase in atomic radius down the group. You can expect many questions from this topic. Don't miss this topic. Watch the video completely so that you get all points cleared. And if you think the video is useful, do like the video, share the video with your friends, and also leave your feedbacks as comments in the comment box below. If you have not yet subscribed my channel, do subscribe it now and support me. Press the bell button and all button near it so that you get intimated as soon as new videos are posted. Thank you very much. Come, let us start the class. Now we will see the periodic trend. In the previous videos, we have already discussed the definition for atomic radius and also how it is measured. We have also seen the types of atomic radii. In general, the atomic radius goes on decreasing within a period, that is as we move from left to right, excepting for the 18th group or the zero group. And within a group, it goes on increasing. So on the extreme left hand side, that is the first group elements, which we call alkali metals, have the biggest atomic radius, and on the right hand side, the halogens, that is the 17th group elements, have the smallest radii. The 18th group elements anyway have very large atomic radius. Look at the trend of atomic radius in the second period and down the first group. For convenience, I have given the values of these atomic radii for the second period and the first group, also for the 17th and 18th group. The values of atomic radius is given in picometer. In the second period, the atomic number of lithium is 3, beryllium 4, boron 5, carbon 6, nitrogen 7, oxygen 8, fluorine 9, neon 10. Neon belongs to the 18th group, that is zero group, and fluorine belongs to halogen group, that is 17th group. Lithium belongs to the first group, that is alkali metals. Across the period and down the group, atomic number increases, but the trend of atomic size will be different. Across the second period, when the atomic number increases, the atomic size decreases up to nitrogen. This is with reference to the second period. You can note here the atomic size of lithium is 152 and that of nitrogen is 70. After that, the atomic size of oxygen is greater than that of nitrogen. Again, for fluorine, the atomic size decreases. Neon belongs to zero group. Its atomic size is much greater than that of fluorine. So we find that there is some anomaly in the atomic size of second period elements. What is the reason for this? But before we answer this question, let us see the trend of atomic radius down the group. Let us take up the first group. Atomic number of sodium is 11, that of potassium is 19, rubidium it is 37, cesium it is 55. Down the group, the atomic number increases by a large value and the atomic size also increases steadily. So the trend of atomic radius is diametrically opposite in the period as well as down the group. That is, when it increases down the group, it decreases across the period. For the second period elements, there are 2 shells, whereas for the third period, that is for sodium, there are 3 shells, and for potassium, which is in the fourth period, has 4 shells. So down the group, the number of shells go on increasing. You need to remember this point also, because we need this point when we start discussing the reason for the trend of atomic radii across the period and down the group. In the diagrammatic representation of the atoms belonging to the period and the group, I have shown the size of the atomic radius and not the atomic number or the number of neutrons. The unit is picometer. Now we will proceed to see the graphical representation of the variation of the atomic radii along the period and down the group. I have already prepared the graphical representation of variation of atomic radius with increase in atomic number across the period and down the group. We know that across the period, when the atomic number increases, the atomic radius decreases, and down the group, atomic radius increases with increase in atomic number. This graphical representation is for second period and first group. The shape of the graph across the period and down the group is different. First of all, we will see the trend across the period. As we move from lithium to fluorine, the atomic radius goes on decreasing. There is a steady decrease up to nitrogen. Then for oxygen, it slightly increases, and then fluorine, it further decreases. As I have already told you, these measurements are all in picometer. Now let us see the shape down the group. Down the group, it is lithium, sodium, potassium, rubidium, cesium. The atomic radius goes on increasing from top to bottom. For cesium, it is 262. For lithium, it is 152. Up to potassium, there is a steep increase. After potassium, the increase is a little less. So for across the period, the graph is directed downward, and for the group it is directed upward. Now we will proceed to understand the reason for the anomalous behavior of certain elements belonging to period 2 with reference to atomic radius, and also the reason for the steady increase in the atomic radius down the group. In order to understand the reason for the variation in the atomic radius, that is anomalous variation in the atomic radius of second period elements, we will first understand the factors which decide the size of the atom across the period. First one, inter-electron repulsion, that is the repulsion among the electrons, especially the valence shell electrons. Second one, the nuclear electron attraction. All the positively charged protons are concentrated in the nucleus, so the nucleus is positively charged. The electrons are negatively charged, so they attract. It is the combined effect of these two forces, that is repulsive force and attractive force, which decides the size of the atom. If the inter-electron repulsion, that is the repulsion among the electrons, is more, there is every chance of the atom becoming slightly bigger. On the other hand, if the nuclear electron attraction is more, then the electrons are pulled towards the nucleus and the size of the atom decreases. Across the period, the additional electron always moves into the same valence shell. The number of shell does not increase in a period. So as we move from left to right, the repulsive force increases. But remember, as we move from left to right, the number of positive charges, that is the number of protons within the nucleus, also increases. The mass of a proton is equal to 1 U, whereas the mass of electron is negligible. Therefore, as we move from left to right along the period, we find that the attractive force of nucleus on the electron will be more than the repulsive force among the electrons. This is what happens up to nitrogen. Moreover, in the case of nitrogen, the 2p orbital, The p orbital has a capacity to hold 6 electrons, but in the case of nitrogen, there are only 3 electrons in the 2p orbital. Therefore, repulsion is much less. So, from lithium to nitrogen, the nuclear electron attraction overweighs the inter-electron repulsion, causing a progressive reduction in the size of the atomic radius up to nitrogen. This is the electron configuration of nitrogen, atomic number 7. 1s2, 2s2, 2px1, 2py1, 2pz1. So, electron repulsion is much less. The 3 electrons in the p orbital are oriented in 3 different directions. From nitrogen to oxygen, there is an increase in atomic radius. Let us see why it is so. The electronic configuration of oxygen 8 is 1s2, 2s2, 2px2, 2py1, 2pz1. So in oxygen, the p orbital has 4 electrons. So the additional electron may remain in the x, y or z orientation. Here I have shown it in the x orientation. So the electron repulsion will be more than the repulsion in the case of nitrogen, in spite of increase in nuclear charge. So in the case of oxygen, the inter-electron repulsion overweighs the nuclear electron attraction. So its atomic radius slightly increases. Now for fluorine, atomic number 9. The electron configuration is 1s2, 2s2, 2px2, 2py2 and 2pz1. So the p subshell has 5 electrons here. Therefore, electronic repulsion increases. But there are 9 positive charges in the nucleus. Therefore, the nuclear charge increases. Here in the case of fluorine, the nuclear attraction overweighs the electronic repulsion. Therefore, the atomic radius slightly decreases. From fluorine to neon, the atomic radius increases sharply. Neon, atomic number 10. The electronic configuration is 1s2, 2s2, 2px2, 2py2, 2pz2. The p orbital is fully filled here. There are 6 electrons. The electronic repulsion outweighs nuclear attraction. So the atomic radii sharply increase. Neon is an inert gas, and for all inert gases, the atomic radius is considered in terms of van der Waals radius because they are non-reactive. You have already learned that van der Waals radius is always greater than covalent radius. Hope you have understood the reason for the anomaly in the atomic radii size of certain elements in period 2. Now let us go on to explain why the atomic radius increases down the group. From the readings given, you understand the atomic radius steadily increases down the group. What are the factors which decide the atomic size down the group? Number 1, inter-electronic repulsion. Second one, nuclear electronic attraction. This factor depends upon nuclear charge. When nuclear charge increases, nuclear electron attraction also increases. Third one, shielding effect. The combined effect of all these 3 forces decide the size of an atom or the radius of the atom down the group. In the case of down the group, the additional electrons go into subsequent shells. That is, when the second period elements have 2 shells, the third period elements have 3 shells, fourth period elements have 4 shells, and so on. The number of shells increase by 1 down the group. There are electrons in the inner shells as well as in the outer shells. What is shielding effect? The inner shells will be slightly smaller in radius than the outer shells. Electrons in the inner shell will prevent or hide or shield the outer electrons from nuclear attraction. This is called shielding effect. Shielding effect is caused by the inner shell electrons. As the number of shells increase, the shielding effect also increases. So the valence electrons are less attracted by the nucleus. In other words, the effective nuclear charge on the outer shell electrons, that is valence electrons, will be reduced very much. At the same time, electronic repulsion will be more. Therefore, even if the nuclear charge increases with increase in atomic number due to the shielding effect, the outermost electrons are more or less free and their repulsion also is more. So the atom tends to be bigger. That is, the atomic radius tends to be bigger and bigger as you go down the group. I hope these points are quite clear. Before we wind up this video, I want to add one more point here. So far we were talking about the covalent radius. When we come to van der Waals radius, the van der Waals radius also goes on decreasing across the period. For example, the van der Waals radius for nitrogen, oxygen and fluorine is 150 picometer, 140 picometer and 135 picometer respectively. Similarly, van der Waals radius increases down the group. For example, for chlorine, bromine and iodine, that is 17th group, the van der Waals radius is 180, 195 and 215 picometer respectively. When we come to the zero group, their atomic radius is always greater than that of the preceding group, that is the 17th group. Reasons have already been discussed. And within the zero group also, the van der Waals radius goes on increasing. For example, the van der Waals radius, which is the atomic radius for helium, neon, argon, krypton and xenon, is equal to 120, 160, 191, 200 and 220 picometer respectively. With this, we have completed the discussion on periodic trend of atomic radius. Do not forget to subscribe and like and also leave your feedbacks as comments in the comment box below. Please share the video with your friends who may also be benefited. Thank you very much. We will meet in the next video with next important topic, that is next periodic property. Till then, bye. Take care.